Here we're back, continuing talking about multiple integration. Alright, now we want to look at using multiple integration to find the area of a triangle. In our previous video, we use it to find the area of a rectangle. Now here, this triangle consists of a slanted line. That line would be, well, the equation of that line could be, well, it would be in the form of a straight line. Y equals mx plus c. Now imagine that this starts at 0, so c would be 0. So you could say this is y equal, let's just say mx. Alright? Now, a question like this would ask you to find the area bounded by the x-axis, the line x equal to something, right? Call it x2, some number, and the curve, well, it's really a straight line, but you may say the curve y equals mx. Alright? What we're going to do is look at this generally, and then we look at an example with numbers. So what you do, you have, remember that you have these squares. Let me put one down here. The width is delta x. I use delta because it's not fixed. It's going to be changing, right? Getting smaller and smaller. The height is delta y. So we put a rectangle, a square here. Alright, let's put it here. There's some overlapping, but you get the idea. We have another one here. Well, only one is there. Only one is here. We are stacking up from left to right, but let's say we're stacking them up from bottom to top. It's kind of hard to get this one without disturbing the triangle. Alright, so what we're doing, we're adding up from, let's say at the bottom we have y equals y1, and at the top y equals y2. We're stacking up from y equals y1. In other words, we're adding up from y equals y1 to y equals y2, whatever that is. And what we're doing is adding the delta y's upwards, so it's delta y. So that is the height. Alright? Now, as we keep stacking them up, we have one here. Let's put another one here. You know, part of it goes outside. Then after that, we need to have more of them to the left in order to fill out the entire triangle. So we have one, other one here, another one here. We could get rid of one of these squares, right? And then we have our next one here. So we're piling them up sideways now. Alright? Piling them up sideways. In other words, we're adding up the width. So we're adding up from y, from x, I mean, not y. X is equal to, if we're looking at it from left to right, and x1 is here, x2, x1 to x2. Alright? We could consider the right as x2 and the left as the right as x1 and the left as x2, but let's say we're moving from left to right. And what we're doing is adding up sideways. What we're doing is adding up the width, delta x. Now, you know, half base times height is the thing there, the area of a triangle. But we're not going to consider that right now. What we're doing, right, is considering what y2 is. What is y2? That's interesting. The y2 went up here on the right. If we start on the left, the y2 will be small. Start on the right, the y2 will be largest. And the y2 keeps increasing, right? More and more. So the y2 is not fixed, right? Oh my, I didn't want to move the, what's going on? I don't want to move the triangle. It's kind of difficult navigating this thing without interfering with the triangle, right? But, right, keep happening. I want to touch this and not interfere with the triangle. But anyway, the problem here that we're having is that the y2 keeps changing. So things have got more complicated now than they were before. With the rectangle, you just have one y2. It's just fixed. I didn't have to worry about any changing y's, right? But now it keeps changing. Now, we've stacked up the entire triangle. But how is it going to happen here? Let's see something. What we're doing is we're adding up the x's from x1 to x2, and it is delta x that we're adding up. And then when we do, we're also adding up. Let's add the y's first. So we're going to move this. We're adding up the y's from y1 to y2, and the height, we're stacking up the heights from the floor to the ceiling. Delta y, y not x. And when we do that, these columns that go up, we're adding them up from left to right. So now we're adding the x's, and it is the width that we keep adding. We're adding delta x's from left to right. Now the function here, unlike the rectangle, is not going to be 1 that we have. Oh yeah man, it's 1. I'm confusing myself. It's 1 that we have, but the y2 now is not going to be a fixed number. Now when you go upwards and you touch the ceiling is slanted as if it's the bottom of a stairs, right? It keeps changing. When you go up, what is it that you touch? It is mx, right? It is mx, the gradient times x. So y2 is really something times x. Call it mx, whatever the gradient is. So let's see what's going to happen now as we integrate. When we do the integration for this now, what we're going to say is that these little squares, they get even smaller, so that the width delta x approaches 0 and the height delta y approaches 0. So the number of them you need get bigger and bigger and approach infinity. So at this point, you change the summation sign to integral sign. You integrate from y1 to y2. In other words, from y1 to mx, whatever that is, of delta y, oh, not delta y, dy, because we changed to d, and you integrate from x1 to x2 dx, and integrate 1 there. Now, oh, this rectangle was from our previous work. Alright, so here, let's integrate this from y1 to mx. Now, when you integrate with respect to y, you get y. And this is a definite integration. It goes from y1 to, well, by the way, what is y1? Let's not leave that out. Y1 is 0. Alright, it's 0. It is 0. Because we're starting on the floor, on the x-axis. So you can just call y1 0. Right? Now, that will simplify what we're doing. Right? But let's do it later on. Let's not do it just yet. From y1 to mx. And we're integrating this from x1 to x2 dx. So what this is the integral from x1 to x2 dx. But what happened between is going to be y becomes mx minus y1. Alright, now we know that y1 is 0. So what we're doing is integrating mx from x1 to x2 dx. Now what is that? Well, x2 would be, well, I mean, when, not x2, when you integrate mx, you get mx squared over 2, right? And you're going from x1 to x2. So what is that now? Let's do it under here. You substitute this first value for x, so you go m times x2 squared over 2 minus lower boundary m times x1 squared over 2. But what is x1? Well, we started at 0, so x1 is 0. So that simplifies our expression here. So it's m gradient times x2 squared over 2 minus 0. So this is half mx, right? Now, this is half mx. Now here, half mx is going to be what we get for the area of this thing here, this rectangle. So here now, we're going, remember what we did? Or from x, we go from y1 to mx, right? There's mx minus y1, this is mx minus 0, right? And then we integrate this, so mx squared over 2. So when we do mx squared over, mx squared x2 squared, I had left out the squared part of it, right? So it's m times x2 squared over 2 that you get. You see that? Now, if you leave out the m for now, right, the gradient, remember it is y equals mx plus c, right? In our case, y equals mx. Alright. Here, if y is mx, y is the, let me put it this way. Half mx times x, that is x squared, alright? So y is mx. Did I say leave out the m for now? It was my mistake. Yeah, we keep the m, but we're going to drop the 2, leave out the 2, the x2 for now. Alright, just deal with x. The x2, by the way, x2 would be the width, right? x2 will be the width. So let's call this the width. Half this here, y column x, would be the y, right, times this is x2. Both of them are x2 still, you know, right? But at this point, y is equal to m times x times the width x. So this is the height, this is the width, so you can consider this half, let's put the x here, xy equal half times the width times the height. Sometimes we call the width the base, half waist times height. Alright? We're going to look at a specific example in our next video, so I'll see you then.